Okay, so I am going to do a problem where we're going to use an ice table to figure out some equilibrium concentrations, and we're given K. So in the problem, we're given K is equal to 0.016. Okay, and we need to figure out what the equilibrium concentrations of everything are. So the first piece of information we're given is that we're introducing 1 mole of HI into a 5-liter flask, and this will give you 0.2 molar. Okay, so we know our initial concentration of HI. It's given to us in the problem. What we don't know is the change in the equilibrium concentrations. And so we're going to introduce our HI into our flask. Under initial conditions, we have 0 molar H2 and we have 0 molar I2. And I'm using arrows to point to what these refer to because they're not exactly under each component in the ice table. Okay, so we've got our initial conditions. We know that the H2 and I2 are going to go up some amount. We're going to say that's X. When it changes toward equilibrium. Okay, and we also know that our HI is going to go down by 2 times whatever X goes up because of this 2. Okay, so every mole of H2 and I2 that's produced, you're going to get 2 HIs decreasing. So that's what that 2 is saying. And then at equilibrium, we just add those 2 rows together. And I'm going to put my units in there. Okay. Okay. So I've got my equilibrium concentrations with an unknown in it. And I can say that my equilibrium expression is this. Right? So now I can substitute my equilibrium concentrations in there. So this is X times X. I'm going to leave units out because just to kind of simplify what I'm writing down. And this is 0.2 minus 2X, right? Okay. This simplifies to X squared over 0. Oh, sorry, there's a squared there too. So I had missed that before. X squared over 0.2 minus 2x squared. Now this all, I'm going to start on the next line here, this x squared over 0.2 minus 2x squared is all equal to 0.016. So what we can do is we can take the square root of both sides of this, and let's just write it down here on the lower line. What that gives you is x over 0.2 minus 2x equals the square root of 0.16, which equals 0.13. Okay. So now what I've given myself is a simplified algebraic expression that tells me how my concentrations are related to some equilibrium constant. And because my question is asking me what the equilibrium concentration is, or sorry, what the equilibrium composition is, which means all of the concentrations on that line there, I can simplify this further to find X. And I need to plug X into all of these 3 equations to get my equilibrium composition. Okay, so I'm going to first do this. I'm going to multiply both sides by 0.2 minus 2x. Okay, and that gets rid of the 0.2 minus 2x on the bottom in the denominator. Okay. And If I multiply 0.13 by 0.2, I'm going to get 0.026. And then I'm going to multiply 0.13 by 2, and that's going to be 0.26x. Okay, so that's what I've got so far. And I want to consolidate this, my x expressions, and get those on the same side of the equation. So I'm going to say x plus 0.26x equals 0.026. This is all algebra from now on. Okay, and so now I can take x, I can factor x out and say that's 1 plus 0.26 equals 0.026, getting closer. So what this ends up being is 1.26x. I've just added my 1 and my 0.26 together to get that, equals 0.026. So now all I have to do to find x is to take 0.026 and divide it by 1.26. So I'll do that. And I end up with 0.021. And the units on that are molar, because x stands for concentration of specifically of H2 and I2. So we know that H2 equals I2, which equals 0.021 molar. So we've gotten that part of the equilibrium concentration, or composition, I should say. And then we know that HI, the equilibrium HI concentration is, from our table above, 0.20 minus 2 times this x value, which happens to be 0.021. Okay, and so that ends up being 0.16 molar. Okay, so that's my equilibrium concentration. That's my equilibrium constant. I can't even say it. That's my equilibrium composition. I have 0.021 molar H2, 0.21 molar I2, and 0.16 molar HI. Now let's go back up to our Kc and see if this makes sense. Our Kc is less than 1. Okay, it's a relatively small number. Does it make sense that given that we have more products than, or sorry, more reactants than products, does it make sense that Kc would be small? And if we look back at our equilibrium expression, let's look at that. So our Kc is small. That means that the denominator here is going to be larger than the numerator to get a small value for our Kc. So larger, smaller, to get a small Kc. And is that the case? Yes, that is the case, because we have our larger value for our reactant and our smaller value for our products. So this equilibrium favors the reactants. It's a small k, and we see that actually through the equilibrium concentrations that we have calculated.